After this, we'll be free, all of you will be free to watch the match, Brazil and Serbia. Let's see what is happening. Well, now we have Professor Felipe Fanchini. He's from UNESP, University of Júlio
de Mesquita Filho.
Júlio de Mesquita Filho, in the state of São Paulo, UNESP. He got his master and his PhD in Institute of Physics in São Carlos, and now he's professor in UNESP. He has been working with quantum information since the last 2 decades, and quantum computation, and so on. And now, more recently, he started working with quantum machine learning, classical machine learning, and this is the subject of his talk. Thank you very much for accepting the invitation.
Thank you. Okay, so first of all, I'd like to thank you for the opportunity to stay here today and to talk a little bit about our work. Since we are in a school, I will take part of this talk to give an introduction about errors, why noise intermediate scale quantum device is important nowadays. I will talk a little bit about classical machine learning and also quantum machine learning. Of course, that it will be quite briefly, but I think that it will be interesting. Okay. This work was developed with the team of NTT Data. It's a company, multinational company of technology. There's a lot of people because, in fact, we don't understand too much about question answering, calibrating question answering. So, and even machine learning, classical machine learning, of course, it's not my expertise, but it's the expertise of this team. So it's a lot of people. It was not online yet, but I hope yet this year it will be there. Okay, so just to give a summary, I will talk a little bit about the timeline of quantum computing, just an introduction, and the noise intermediate scale quantum devices, classical machine learning, quantum machine learning, and then more specifically BERT, that's a model for natural language processing, and how we use quantum machine learning to calibrate question answer systems. This will be the line of our talk today. Okay, just to give an introduction about the timeline of quantum computing. I intend to do this because in general, when I read these timelines, we always listen that Feynman was the guy that created these ideas, but in fact, it's before Feynman. So it began in the 1970s. We have also the first papers that I believe that begin this idea is the Poplawski from 1975 that talk about thermodynamical models of information processing. And there's other researchers that also work on it, even before the 1981, the year that Feynman gives that talk where they introduce for the community these ideas, in fact. So we have also 1918, Paul Benioff talking about Turing machines and using Schrödinger equation. Yuri Manin, that's a Russian guy that's beginning with the idea of quantum computing. Hopefully, in 1981, then we have also Paul Benioff and Feynman in the talk in the Conference of Physics at MIT, where it is the most cited beginning of the idea of quantum computing. There's more, of course. In 1985, Deutsch introduced an algorithm. 1983, there is another famous algorithm from Bernstein Vazirani. In 1994, we have the boom of the quantum computing with the algorithm of Peter Shor for decomposition into prime terms. We have the first implementation, 1995, Love Grover with the quantum search algorithm, Knew and Laflamme in 1996 with quantum error correction, Then in 1998, the first implementation of Grover algorithm. 2001, the implementation of the short algorithm. And in 2012, John Preskill then introduced the idea of quantum supremacy. He coined this term, quantum supremacy. And in 2018, John Preskill also termed the coin noisy intermediate scale quantum devices. So the idea here is to try to find some useful task for computers with few qubits, and they are also qubits that are subject to errors. So this idea began in 2018, and of course, 2019, you have the supremacy reached from the Google team. 2021, the Chinese group from PAN, also with using Gaussian boson, they also reached the quantum supremacy. And nowadays, there is a lot of research in noise intermediate scale quantum devices. That's called the noise intermediate scale quantum era. Okay, this is the timeline that I believe that's fair enough to introduce. Okay, NISQ era. From NISQ era, I think that the most famous algorithms are the variational quantum algorithms. We have variational quantum eigensolvers. We have a quantum approximation optimization algorithm, QAOA, quite famous nowadays, and variational quantum machine learning. That's what I use here to develop our work. But there's more than this. We have also, just to conclude, variational quantum algorithms are the most used, but there's more than this. Then we have quantum annealing, Gaussian boson sampling, that the group from Chinese reached the supremacy, analog quantum simulation, digital analog quantum simulations. These are some algorithms that are inside this NISQ era. If you'd like to make questions during my presentation, please, let's do it. Yeah?
Sorry about my ignorance, but you mentioned something about quantum supremacy. This term was coined by John Preskill.
Yes.
Yes. And what do you mean now when you said that
the Chinese group, they reached this quantum supremacy.
What do you mean by this?
They found an algorithm that you cannot implement in a classical computer. It's impossible because, at least nowadays, we're using classical computing. This is the idea of the quantum supremacy. Good question, thank you. So, the main point here is, if you'd like to find a review, please, there is a recent one published in February. It's a review of modern physics, 94, noise intermediate scale quantum algorithms. This is a good review. It's nice. Okay, I think that just leave this and use this space. Okay, so why NISQ devices? So I try to explain why it's important nowadays to try and find algorithms that works in these kind of machines. So I just propose an example. Suppose that we have this algorithm. We have quantum computer, 1 qubit quantum computer, and then you initialize it on 0. Then you apply bit flips. If you have a bit flip, it will just flip from 1, 2 bit flips, it will return to 0, 3 bit flips, 4 bit flips, then you just rotate your qubits from 0 to 1 if you apply a sequence of bit flips gates. So in an ideal situation, you reach something like this. The expectation value of the sigma z will be -1, 1, -1, 1, -1, 1. This is the ideal situation. But unfortunately, it's not what we reach in a real quantum computer. There is some kind of errors that are present in these machines, and we need to learn how to treat and how to work with it. Some kind of error that's quite common is called coherent error. It's not related with noise, environment. It's just a control error. Sometimes you intend to do a bit flip, but it's it's a bit more than a bit flip. So you don't stop in the right position. And if you have some epsilon that is more, it's a cumulative problem. And in the end, what you find is something like this. It's quite complicated because if you don't have a perfect control, the expectation value begins to oscillate, and it's a kind of problem. From variational quantum algorithms, it's not a big problem because when you try to determine your parameters, you can take into account this. So for variational quantum algorithms, it's not a problem, in fact. But if you intend to do usual or common algorithms like Shor, certainly it will be a big problem. And of course, it's present in real computers. It's not easy to do a perfect rotation in a qubit. But there's more than this. You also have environment noise. For example, if you introduce bit flip, then situations get even worse. And more errors are introduced to your system. Another critical error is an error called readout assigned error. Is an error when you try to read your qubits. If you have a look in a real computer from IBM, for example, this is your number, 7.6, 10 to -3. This is your error when you try to do readout assignment. So why it's so crucial? Because even I don't begin to do a calculation. I just try to prepare and measure the qubits. If you do this with 1 qubit, you have this amount of error. But if you introduce more and more qubits, I don't do any kind of calculation, just prepare and measure. And what we find is very critical. The purity of your system just goes to 0 when you have 200 qubits. So it's an enormous problem. I don't do any kind of calculation. Just prepare and measure the sequence of qubits. Just for 200 qubits, the purity almost reaches 0 without any kind of algorithm implemented. So it's a big problem. And this one is the best qubit that IBM has. If you have the second qubit in this machine, this error is even bigger than the other one. So it's quite complicated to do this. And it's important to note that quite recently you have this paper, 10 days ago, I think so, less. A group from Microsoft and HEG tried to estimate the number of qubits that you need to implement these some algorithms. In the case, they tried to implement 3 kinds of algorithms, quantum dynamics of a transverse Ising model, quantum chemistry, and also the last one is the Shor algorithm. And these are the numbers of qubits that you need to do this. It's in millions of qubits. So we are talking 200 here, and you need around 1,000 or millions of qubits to do this kind of algorithm. So it's a difficult task to be implemented. Life is not easy. In fact, for quantum computer scientists, it's even worse. OK, so this is a motivation why we are trying to find some algorithms that works in small scale and also noisy qubits. Because if you would like to wait for millions of qubits, we need certainly a breakthrough in the area because it will be not so easy to do this. This motivates the NISQ devices. OK. Well, since I tried to use this NISQ device to implement quantum machine learning, I think that's important to talk a little bit about classical machine learning, just to introduce. It's a computer science area. There's a long time that people do this. So here, I think that the great majority are physicists. So I intend to just give a brief introduction. What is the machine learning? So classical machine learning begins with this kind of table. We have a table, and we have a lot of features. And the idea is to try to determine this target. As a feature, you can imagine some characteristics of a problem. For example, if in our case we are trying to calibrating answering question, we have the number of words in the question, the numbers of words in the answer, the first word in the answer, the last word in the answer, and this gives your features. Then you try to determine a target, for example, the probability to be a right answer. This is the idea. Of course that you can do this for many tasks in the world. From churn problem, for example, when people would like to leave your company to go to another one. If you looked for the history of the transactions in a bank, then you can try to predict if your client will change for another company, and there's much more than this. Okay, so the idea is to include these features in a vector and introduce your target in a variable. So the ingredients are the data, that are this vector with a set of features and a target, and then you need also a model. This model is the mathematical model that will connect your vector with your target. It could be quite different. You need to be creative. You can create many, many different models. Just to try to exemplify, the simplest one is the linear mode. For example, suppose that you have a problem with two features, x1, x2, 0.31, 0.44, and then I try to reach an answer. Then I need to calibrate these parameters, theta 1, theta 2, since that once you multiply, you reach the answer. And of course, this theta 2, theta 1, and theta 2 should work for all your data sets. So you fix this, and then you try to find the best parameter as possible, since that given a vector, I multiply by this, and then I reach your target. Of course, that it will be not 100%, at least it's not so common, but you try to minimize the errors in all your data sets. You need to find the best solution. So it's a minimization problem or a maximization problem to find this pair of parameters that connect your features with your answer. This is the simple problem that you can find. Of course, that is much more complicated when you try to work with real machine learning. And the last step is the cost function. The cost function just is a measure of how far you are from your target. So for example, mean square error is a kind of cost function that you can use to check how far you are. You need to minimize this cost function for all your data. Then you reach an algorithm that can predict for new data. This is how it works. It's important to emphasize that in general, given your data set, you separate in two parts. This training data you use to determine the thetas, the parameters. And once you determine minimizing your cost function, then you test with the rest of your data set to see if it works well. So when you train, you never use this red part. You just use this, try to reach the best one, and then once you find it, you test with the rest of your data set to see if it works well. This is the idea of the machine learning, classical machine learning. So just to skim this problem, we have a training data, we have a model, then we calculate a cost function. Of course, that when you begin with some random theta, it will not be good. Then what you do is to calculate some optimization problem. For example, calculate the gradient descendants, compute gradients. Then you actualize your vector, and then you begin again. Then you do this until you find the best set of parameters to optimize your model. Once you find it, then you can test in the rest of your data set. Then you take the test data, you choose the best parameters that you find, and then you compare the answer with the right one. And then this gives the probability or the accuracy of your machine learning algorithm. This is the main idea concerning machine learning. Yes?
Your solution typically is some kind of approximation to the real answer of the problem.
Exactly. It's, you try taking all of your data set to find a set of parameters that approximate all them as better as possible.
I have the following doubt. You start with some data that you have, you feed this, you start moving on with the program, and you find another candidate and evaluate if the...
Then you calculate again, check again, optimize it, try a different one, check again. Then you do this, you find this optimization until you reach this set of parameters. Once you find this set of parameters, then it's quite easy to implement because there's no more calculations. Just a multiply matrix using this set of parameters, and then you can have an answer. So to train is quite difficult. To test is quite easy.
Might be that this process does not converge or not?
They will convert for some probability. If it's good enough, it's not, I don't know. It depends of your problem, yeah? But they can reach 99% of precision, but again, it depends of the problem. You can have 8% or 50% that just play a coin, and also depends of the problem.
And one more doubt.
Please.
If you run this, after 3 runs, for example, you already forgot what was your initial data. You're not working with the actual data.
No, you use your training data all the time. You actualize and you try for all of them again. Then you actualize the set of parameters and you test for all of them again. And then you do this until you find the best set of parameters that minimize the cost function. This is the idea. Okay? Okay, so this is the classical machine learning. What about quantum machine learning? What is the difference when we're talking about quantum machine learning? In fact, it's different ways to do quantum machine learning. You can have classical data processed in a classical computer. This is a classical machine learning, in fact. But you can have quantum data processed in a classical computer, quantum data processed in a quantum computer, and classical data processed in a quantum computer. This one is the test that will work here. In general, this is the main subject when you're talking about quantum machine learning. But it's not the unique one, of course. There's more than this. But the idea is to take some classical data and try to change part of that scheme to use some quantum processing to find the answer. So giving this, using this classical data processed in a quantum computer, where is the quantum part? Where we introduce the quantum part in this protocol? And the main point is that you change the model. So the model is calculated in a quantum computer. This is the main idea. We change this classical model for a quantum model. Then you need some way to take your classical information. Then you need to codify in a quantum information. You use some unitary operations parameterized by this theta. And you measure. Then you take classical information again. Then you just continue. Cost function, compute gradients, update theta. And again. Just we change this model for a quantum computer. This is the idea when you're talking about classical data processed in a quantum computer. This is what we will do. So how we can do it? So as we said, we change the model for a variational circuit. This is the main idea. So here's the steps for training in a quantum computer. This is our model, a quantum model. So the first step is to encode the classical data in a quantum state. Then you need to apply a parameterized model. And in the end, you need to measure the qubits to get the labels. There is many different strategies to do this as well. For example, when you're talking about encode classical data, you have different ways to do this: basis encoding, amplitude encoding, ongoing encoding. Here, I will just give an introduction about ongoing encoding. So the idea is the following. You just take all your initial qubits as 0, and then for each one of your feature, x1, x2, x3, xn, is your vector. This is a feature, the set of features that you have. So you introduce x1, a rotation x, for example, it could be y, but we choose here x, rx, x2, x3, xn. So your feature determines how you will turn your qubit. This is the idea to encode the data in a quantum computer. As I said, there is many other different ways, but we don't have time enough, so I just give this idea. Then we need to apply a parameterized model. This also is rich. You can have many different kinds of parameterized model. As example, if you have this archive, you have here, for example, 19 circuits that you can use to parameterize. Here, each one of these gates has a parameter. So they don't include the parameters here, but understand that here is a theta 1, theta 2, theta 3, theta 4, 5, 6, and so it's a lot of parameters that you need to calibrate it to have the best answer. And the best algorithm to do is, nowadays, we don't know. We are just testing different ones and trying to check what's the best circuit that you can use to parameterize your model. This is a test and try. The idea of this parameterized is to try to take the high expressibility possible. What means? The idea is that you need to take an initial state, and if you take random parameters, the idea is that we can try to access the Hilbert space as big as possible. You need to try to reach many different parts of your Hilbert space. So for example, in this circuit, if you take just one parameter theta 1 here, you just need states around this part of your sphere. If you have this algorithm with 2 parameters, you see that they are concentrated here and here. But if you take arbitrary unitary, you can reach all your Hilbert space. But also, there is no rule about it. There is no concrete idea that high expressibility, you'll be better. No, it's not also proven that it's true. So people think that's true, but in fact, there are some counterexamples that shows that high expressibility do not mean high accuracy for your model. So this is the second step. And the third one is to measure the qubits to get the labels. Also, there is different strategy. You can measure, for example, just the first qubit, or you can measure all your qubits. So this is called an M strategy, and this is a full KNN or full measure, full strategy. And also, you can try and you can check if it's what's the best situation. It's important to emphasize that this parameterized mode you can repeat. So you have different layers, many layers. One layer, then you repeat again with more 5 parameters. Then you introduce more with 15, 20, 25. So you can increase the depth of your circuit. Here, just introduce one. But it's important to emphasize that you can take this parameterized model and make more and more layers to try to find the best solution. So this is the idea about the quantum machine learning. In our studies, we will work with full KNN. So we will measure all these qubits. It's important to note that when you measure all these qubits, you have, in fact, for example, if you have 5 qubits, we have 5 parameters. If you want to take these 5 parameters or 5 answers and transform it in one answer, then you need to introduce it in another classical machine learning to take these answers and then try again to transform him to take a final answer that you gives, for example, probability of to be right or wrong. Okay, so here is our scheme. We just change the model with this kind of circuit, and then we continue. There is also strategies to compute gradient. It's quite important because it's not easy, but there is some trick to do this in a quantum computer. I will not take the details here, but it's important to say that for quantum algorithms, it's easier to calculate these gradients when you use parameterized quantum circuits. Okay, so finally, let's talk about our work. So the idea here is to use this strategy to calibrate in question-answer systems, and we will try to do this with quantum neural networks. Calibrating question-answer is important because, it's important because, in general, depends of your algorithm, the answer is not well calibrated. What it means? Sometimes your algorithm said that if you are driving a self-driving car, they could say, okay, you can go, but in fact they commit a mistake. Oh my God, this is a mistake, you should stop it. So it's a problem. So it's need to calibrate the answer to check if it's underestimated or overestimated. And they use another machine learning just to calibrate your answer. And for question-answer systems, it's quite important. Well, there is some algorithms to do question-answer systems. The BERT algorithm is probably the most famous. It was developed by the Google team. And probably you never hear it, but you use it all the time. If you go in the Google and make a question, it gives you a suggested answer. This is BERT working. When you try to write an email and they suggest a word for you, this is a BERT algorithm also work. When you receive an email and there's that suggested answers, this is BERT algorithm working. So they developed this in 2018, and everybody nowadays use it. It's developed by the Google AI team. So it's a really breakthrough in the area. They use, for example, 340 million parameters to train this algorithm. They use the full internet to calibrate these algorithms. Not the Wikipedia, but they use books, all the sites, everything, just to calibrate this pre-training. And once you train, then you have these 340 million parameters determined, then you just use it to make new suggestions. For short, this is an unsupervised learning, so you don't need a human to check it. And this works something like this. They just take a text and they remove some words, and they ask for the algorithm to try to predict what's the word that is missing. And then they, of course, that in the beginning they don't reach a good success, but when you use millions and millions of texts, then they begin to determine what's the right answer, what the right word that you put to complete your sentence. There's some other new ones. There's the NVIDIA right now. It's 8 billions of parameters. And here there is from the Facebook, that's a Roberta. Roberta is a change in the BERT. It's an upgrade. They just use a little bit more than parameters. And there is this Tilbert that we use in our work. That's a simple algorithm to BERT. Even to use BERT is quite difficult because 240 million parameters, even pre-trained, it's quite complicated to read in your memory and to work. So this is important. The Roberta, that was developed by the Facebook AI research, now Meta AI research, University of Washington also. So they introduced the Roberta, and the Rugging Face, the AI community, just developed this distributed, that's a smaller, faster, cheaper, and lighter version of the BERT. This is the two algorithms that we use in our work. The idea is to take the answer suggested by the Roberta and the Stilbert, and then to calibrate the answer to get the right one, or at least the right probability to be the right answer about your question, over your question. Okay, so calibration of machine learning models is quite important because, as I said, sometimes you have crucial answers, and if you commit a mistake, you can kill some persons. Yes?
How can you compute the cost function when you don't know a word?
They just put some notes for some score for each word. So there's a set of scores that they are digesting. So a number for each word in the dictionary. Okay, this is a kind of uncalibrated, for example, machine learning. So the idea here is that your algorithm said that the answer has 20% of be right. But when you check with different data sets, you see that's not 20, but it's 15. Here you said that it's 60, but when you check, it's not 60, it's 50%. So this is an overestimated calibration. Yeah? So this is the problem. The idea is that you reach this in the middle, because then when you say that's 40, in fact it's 40. When you say that's 80, in fact it's 80. This is the idea to calibrate a machine learning problem. So we use the Squad 2 dataset. This is a dataset that you find in the internet. It's just a dataset with question and answering. And this is an uncalibrated one when you use the Stilbert and the Roberta. I'm sorry. For the Stilbert, you use Squad 2. And for the Roberta, you use an internal entity dataset. So you see that Roberta for the entity dataset is quite uncalibrated. And here also, this expectation calibrated error it's large enough. So you have a problem here because they said that you have here underestimated, here overestimated. So the idea is to try to correct this. So you just include your answer in the Stilbert or Roberta. They give you an answer. And then you take some features of this answer. And then you include in another machine learning, in our case, a quantum machine learning algorithm, to try to calibrate these answers, these probabilities. This is the idea. What about the features? So the features are just 5 features that you need to calibrate. So this is why we can use in a quantum computer, because each feature can be coded in 1 qubit. And the features that we use to calibrate it is the beginning of answer span score. This is a feature that Roberta and the algorithm gives for you. All of them the algorithm gives for you. The end of answer span score, this is the value that I said that they have, a score for each word. The number of words in question, number of words in answer, and also there's a probability there is no answer in your test, in your paragraph. This is the idea. The point is that you have a question, then you take a paragraph and try to find the answer inside this paragraph, and sometimes the answer is not there, so there is a probability the answer is not there. This is the 5 features that you use to calibrate it. So, yeah?
When you mentioned quantum machine learning, and now you're mentioning quantum neural networks, is it the same thing?
Yeah, it's a kind of quantum machine learning algorithm. There's more than this, but this is one of the quantum machine learning algorithms. Okay? It's because machine learning, there is more than neural networks. Neural networks is a kind of machine learning algorithm. Okay, so we use this algorithm to do our task. We use full measurement, just to mention. And here is the a calibrated answer. So you see that before I have something like this, and then in the end they just put the things in the right place. Of course that I don't increase the probability of the answers, but I can say the right probability of each answer. So it's much better than here. You see the expectation calculate error is 0.70, calibration error, and here is 15, and here it was 64. Okay, so this is for the squad 2. If you take the NTT data, this is the calibrated one. Here is a classical calibrator. Here is a quantum calibrator. You see that the classical calibrator also do the task, but here we're showing that the quantum computers can do the same task. And in fact, here is in fact lower than this, but it's almost the same. But if you look for the Roberta answer, it's completely uncalibrated. And here we have the right answer, the calibrated answer of your algorithm. Okay? So this is our work. Just to conclude, so the NISQ area, in my point of view, will certainly be the next step in quantum computing. Given the technology nowadays, it will be quite difficult to reach millions of qubits. Creating robust qubits will be crucial for the development of functional quantum algorithms. This is my view, of course. And what we show is that variational quantum algorithms can be used to calibrate question-answer systems. Just to conclude, a bit of marketing. I'd like to talk about our computation course that we give in Unicamp. For students, you can ask for fellowships. It's working on, we are in our second term now, and if you would like to talk about it, just write me in this email. This is for beginners, but the next year we will have one for advanced that will be for variational quantum algorithms, quantum machine learning, quantum optimization for the next year. Okay, so thank you very much. That's all.
Thank you very much.
Thank
Felipe.
you.
Very nice talk. Questions?
Hi, so thank you, Professor.
Thank you.
When you're running your algorithm, usually you run like your quantum algorithm, and then you get the parameters you measure, and then you change the parameters, and you run it once again, right?
Exactly.
And you do this multiple times until the parameters are good,
Exactly.
right? So I was wondering if, because I never saw it on the literature, I would like to know if there are some ways to get the parameters changing on the fly. Maybe you do some error correction codes to detect where your more weak measurements. Is there something in this area?
Honestly, I don't know. I don't know if they use. Probably.
It seems very intuitive to me that you could maybe try it, at least, right? Theoretically, in principle.
Yeah, at least in principle you can, but I don't know exactly what if they do this. I'm sorry.
Professor, thank you for the presentation. I have, well, could you tell us more details about the calibration using the quantum circuits? Perhaps you showed there a circuit. Is that the one that you're using?
Yes.
The RY gates and then the
yeah.
gates. Is there any reason why you're using it specifically that?
In fact, we try many of them and just take the best one. In general, when you use machine learning, even classical machine learning, it's all of the time you're trying tests, and then you take the best probabilities possible. Because remember that you have some part of your data set that you don't use, and then you try to organize these things that it works as best as possible for your test algorithm. Nowadays, there's some area of quantum machine learning that's called explainable machine learning, that they try to understand why the machine learning trying to find the best results. But it's a quite new area of research. Until very recently, they just try and test, and once you take the best answer, then you use it to make new predictions. Explainable quantum machine learning, I think that's a good idea to research as well.
I think that. And also, well, you are using 5 defined features to train, but those features were really different. One was the start of the word at the start of the sentence. One was if there was a probability that there was no solution. My question is, how did you map that, or how do you encode that information on an angle?
I'm sorry, how I encode the
features on the angles that you use on the quantum circuits?
Okay, you just do, for example, you have a feature that's 0.1, you just rotate 10% your qubit. If your feature is 0.3, you just rotate 0.3, and then you, first, of course, you need to normalize your features from 0 to 1, and then you can just include an angle for each feature. Is what your question?
Yeah.
Okay.
Thank you.
Some professor for the presentation.
Thank you.
I was wondering when you were explaining about how to do the parametrization model, you explain different gates. For example, the Adamar. What happens if you combine the Adamar with a C gate and X gate, and then you plot for a universal gate, and you was saying that that it's not efficient to have a universal gate. I mean, in the case that you can move whatever place in the block sphere. But is it not related with the Gottesman-Neal theorem when you can efficiently simulate a quantum algorithm with a classical computer if you don't have a phase gate?
I don't know if I understand your question. Could you repeat, please?
I mean, that you say that, that you think that there is an open problem with respect to what set of gates you can use in order to do the parametrization model, and you say that if you have a free universal, you have a free movement in the block sphere, it's not efficient to do it?
Yes, well, in fact, what they said is called expressibility, as how you can reach the Hilbert space. But there's some counterexamples where they show that the high expressibility is not good enough as lower expressibility. So there's not a direct relation with the expressibility and the accuracy. We don't know exactly how. It's a beginning area of research, so we don't know exactly why it's not the best. Because if you think, you can say, okay, as if I can reach all the Hilbert space, probably it will be better. But what people are noting is that's not always the right position.
Okay, so one thing is that I was thinking is that maybe in the expressibility, you need to have some phase gates in order to avoid that you can simulate that algorithm with a classical computer polynomically.
Yeah, well, in fact, they use a set of gates, so you can phase bit flips, you can have swaps, control nodes. So this kind of circuit to parameterize it, you can be as rich as you can think. So yeah, you can try different ones, also different number of layers. But nowadays, just as I said, try and test, and check what's the best one for your task. This is the idea.
The last thing is that I was wondering if so you say that the quantum part of this process of the machine learning is in the model, but can it be additionally in the gradient descent process to do it quantically or with a quantum computer?
These gradients that are made in quantum computing, in fact, is the gradient descendant. I will just try to explain, but what they do, it's quite interesting because when you do the calculations, you see that to calculate the gradient, you take your parameters theta, you plus some epsilon, and then you calculate. Then you take these parameters theta minus epsilon, and then you calculate. The difference of these two algorithms is the gradient descendant. you can prove it mathematically.
Yeah,
So,
but do you do it classically with a classical computer?
you calculate these answers in a quantum computer, but you take the difference and then you update your set of parameters, and then you just put it again in the quantum computer to check another round.
My question is, I was just thinking, just an idea,
please.
if you can
Me
do
too.
it with a quantum computer, for example, with an adiabatic quantum computing, that you,
Yes.
you exactly look the optimization or the minimize of a function. In this case would be the cost function, and you use it as a parameter in your quantum computer in order to find, for example, the ground state in the adiabatic quantum computing.
Yeah. If we can show also that if you take, for example, infinite numbers of layers, we will reach exactly the adiabatic quantum computation, for example, for the Quawa algorithm. So, because it's like Trotter, you just take and slice this algorithm, but if you use infinite ones, then one is equivalent to the other. So they are equivalent, in fact.
But you know if there is some physical implementation of quantum machine learning using a quantum computer in the model and also in the gradient descent process?
I don't know, I'm sorry.
Okay, yeah. Thank you.
Yeah.
In the IBM's web page, there are quantum gradient descent.
Yes, they have. They had that implemented there. Yeah, you can calculate. Yeah, sure, of course. Yes, you can. This gradient descendant you can calculate in proper algorithms from the IBM, but they do exactly like this, just plus epsilon, minus epsilon. But there's a problem because, just to conclude, because there's a lot of local minimums. So it's a difficult task because in general you just do not find the best solution. It's a lot. If you take the energy landscape, it's quite noisy, and then in general you just reach a minimum, but it's not the best one. It's quite difficult to optimize these parameters as well. There are some strategies to try to make this surface softy, to try to find the best optimum set of parameters.
More questions? Yeah. Let's thanks again, Professor Felipe.
Thank you.
Thank you very much. So now we have the afternoon free.